In this episode, we're going to be learning slash reviewing some basic arithmetic with matrices. So, for example, matrix addition, subtraction, and scaling, a special operation for matrices called transpose, and then reviewing how to calculate 2 by 2 and 3 by 3 matrix determinants. Okay, so if you have two matrices of exactly the same size, two matrices that have exactly the same number of rows and exactly the same number of columns, two matrices that are compatibly sized can be added together or they can be subtracted from each other. And just like with vector addition and subtraction, if you're adding matrices or subtracting matrices, this is an operation that we do component-wise. So let me give you an example. If I have a matrix that's 2 rows and 3 columns, right from left to right, top to bottom, 2 minus 3, 1, 4, 5, 8. Imagine I want to add that to the 2 by 3 matrix whose entries are 4, 1, minus 6, minus 2, minus 3, 0. The first thing that I'm going to note is that these two matrices are compatibly sized. Both matrices have exactly 2 rows. Both matrices have exactly 3 columns. So I am able to add them together. And to do that, all that I'm going to do is I'm going to add them together entry by entry. So I'm going to add this 2 to this 4. I'm going to add this 3 to this 1. I'm going to add this 1 to this minus 6, and so on. I'm going to add together these matrices entry by entry. And so the result of this is also a matrix with 2 rows and 3 columns. 2 plus 4 giving us 6 for the first entry, negative 3 plus 1 giving us negative 2, 1 plus minus 6 giving us minus 5, and then in the second row, 4 plus minus 2 is 2, 5 plus minus 3 is 2, and 8 plus 0 is 8. So just like vector addition, matrix addition is component-wise, and that is also true of subtraction. So if I took those same matrices, 2 minus 3, 1, 4 minus 3, 8, and I subtracted 4, 1 minus 6, negative 2, negative 3, 0, I would subtract component-wise, and I would do 2 minus 4, result negative 2, minus 3, take away 1, result minus 4, 1 take away minus 6, result 7, 4 take away minus 2, 6, 5 take away minus 3, 8, and 8 take away 0, also 8. So subtraction, once again, is just component-wise. However, if your matrices are not of exactly the same size and shape, they cannot be added or subtracted. So if I had, for example, a 2 by 3 matrix, which I was trying to add with a 2 by 2 matrix, this is not possible. There is a syntax error here. So we would say that this result does not exist, or DNE for short. Now, matrices, just like vectors, can also be scaled. They can be multiplied by real numbers. So for example, if I have the 2 by 2 matrix containing the entries 4 minus 2, 1 minus 1, I can apply a scalar of 3 to that entire matrix. And that would give me the result 3 times 4, result 12, 3 times minus 2, result minus 6, 3 times 1, result 3, 3 times minus 1, result minus 3. So when we scale a matrix, it just happens entry by entry. Let's talk about some of the applications of matrix addition. So a little bit of a side quest into the world of image processing. So for simplicity's sake, let's suppose that we have just a really small black and white image. Now, if the image is black and white, then the color of each pixel can be stored using a single number called the value of the color. So, for example, a pure black color would correspond to a value of 0. A value of 90 would correspond to a sort of medium gray. A value of 180 would correspond to a very light gray, and a value of 240 would correspond to almost white, and a value of 255 would correspond to perfectly pure white. Now imagine that I wanted to take a black and white image and I wanted to brighten it, and I wanted to increase the value of all the pixels in the image. In a case like this, all I would have to do is add a certain number to the values of each of the pixels in this image. So for example, if I represent all the values of all these pixels via a matrix, if I then take that matrix and I add in, for example, the matrix containing 10 in every position, then that will increase the values of all those pixels by 10 units, giving me a result of 190, 10, 250, and 100. And so you can see on the right the colors of the pixels that correspond to these lighter values. So matrix addition gives us a very simple way to brighten images, and likewise matrix subtraction would give us a very simple way to darken an image. And if you don't have a black and white image, these ideas can still be used. You can, for example, use separate matrices to store and manipulate the red values of your pixels, the green values of your pixels, and the blue values of your pixels so that you can bring those values down or push them up to alter the appearance of your image. Let's talk about an operation called matrix transpose. We will be using matrix transpose a little bit toward the end of this class. Now, if you have a matrix called A, the notation for the so-called transpose of the matrix A is A with an exponent of capital T. So this is the notation for matrix transpose. And all that a transpose of a matrix does is takes the matrices rows and turns them into columns and vice versa. So let's take, for example, a matrix A that has 2 rows and 5 columns. So we have 4, 1, 3, 9, 7, for example, and then 0, -1, 5, 4, 2. When we calculate the transpose of the matrix, all that we're going to do is we're going to take this first row and we're going to turn it into a column. And then we're going to take this second row and we're going to turn it into a column. So a transpose is going to have as its first column the values 4, 1, 3, 9, 7. And it's going to have as its second column the values 0, -1, 5, 4, 2. So a matrix transpose just turns rows into columns and vice versa. So if you initially had a matrix like ours, which is 2 by 5, now our matrix is 5 by 2 after taking its transpose. So we won't actually be using that for a little while, but just keep it in the back of your mind. It will come back up at like lesson 37 or 38 or something. Finally, let's go ahead and review determinants for 2 by 2 and 3 by 3 matrices. Determinants, you may have only used them to calculate cross product up to this point, but determinants have far more applications and uses than just cross product. So let's go ahead and write down the general process that is used to find the general determinant of a square matrix. So determinants are something that are calculated only for square matrices. matrices that have the same number of rows as columns. Determinants are not defined and don't make sense for matrices that are rectangular. We're going to focus on the formula for relatively small square matrices, 2 by 2 and 3 by 3. And then much later in the quarter, we are going to talk about the determinants of larger matrices, 4 by 4, 5 by 5, etc., and how to find those. So to begin with, if I want to demonstrate the technique for calculating the determinant of the following 2 by 2 matrix, I can use the following process to do that. So I'm going to start with the very first entry in this matrix, the value positive 1 in the top left corner. I'm going to extract the value positive 1 out of this matrix. And then I'm going to cross out the row and the column containing that 1. And if I cross out the row and the column containing that 1, all that's left behind is this value 4 in the bottom right corner. So I'm going to go ahead and multiply 1 by 4. Having done that with the very first entry in the first row of the matrix, I'm now going to move to the second entry in that top row, and I'm going to do exactly the same thing. I'm going to extract the entry 2, and then I'm going to cross out the row and the column containing that 2. And that's going to leave this entry of 3 in the bottom right corner. So I'm going to take that 2 and multiply it by 3 in the bottom left corner. Then I'm going to go through these two terms and put alternating signs on them. So I'm going to leave 1 times 4 positive, but then as I pass to the next term, I'm going to alternate to negative. So I get here 1 times 4 minus 2 times 3. So I get 4 minus 6, result negative 2. Negative 2 would be the determinant of this matrix. Now, the explanation I'm giving you here for the determinant of this 2 by 2 matrix might be a little bit different than what you learned in Calc 3, for example. But I'm explaining it to you this way because this way of thinking about determinant calculations is the way that's going to scale up and apply to matrices of a larger size. Let's, for example, consider the determinant of this 3 by 3 matrix and talk about how to calculate that. I'm going to use a similar process to what I used in the 2 by 2 case. I'm going to start by considering the very first entry in the matrix, top row, first column. That entry in this case is 1, so I'm going to extract the value of 1 from that position. Then I'm going to cross out the column and the row containing that 1, and I'm going to look at what is left behind in that bottom right corner. And in this case, what's left behind is a smaller 2 by 2 matrix consisting of 5, 6, 8, 9 in that position. So I'm going to multiply 1 by the determinant of that smaller matrix, 5, 6, 8, 9. Then I'm going to pass to the second entry in the top row. So moving over to the number 2 in the top row. I'm going to extract the number 2, and then I'm going to go into the matrix and I'm going to cross out the row and the column containing that 2. And what's left behind, if I cross out that row and column, is another 2 by 2 matrix consisting of 4, 6, 7, 9. So I'll go ahead and multiply 2 by the determinant of that smaller matrix, 4, 6, 7, 9. And then finally, moving to the last row in the last entry in the top row, that contains a 3 in that position. So I will extract that. And then I will go in and cross out the row and the column containing that 3. And that leaves behind this 2 by 2 matrix in the bottom left corner. So I'll multiply by the determinant of that smaller 2 by 2. So that would be the determinant of the matrix 4, 5, 7, 8. Now, just like in the 2 by 2 case, having now extracted these entries along the top row, I'm now going to go in term by term and put down alternating signs between them. So before it was just plus minus, and in this case, it's going to alternate plus minus plus. So now that I've extracted these entries along the top row and expressed everything in terms of 2 by 2 determinants, I can then just go ahead and calculate these 2 by 2 determinants using the same kind of process we established up here in the first demonstration. So, for example, we can expand that first determinant to the form 5, 9 minus 6 times 8. We can expand that second determinant to the form 4 times 9 minus 6 times 7. We can expand that third determinant to the form 4 times 8 minus 5 times 7. And then we just have to PEMDAS our way through this, right? So this is 45 minus 48 in the first brackets. Minus 2 times 36, take away 42 in the next brackets, plus 3 times 32 minus 35 in the final brackets. So that gives us negative 3 minus 2 times, looks like negative 6, and then plus 3 times negative 3. So all in total, that is negative 3 plus 12 minus 9, result 0. And we'll see soon that having a determinant of exactly 0 is a result of some significance. So, perhaps as we explain 2 by 2 and 3 by 3 determinants in this fashion, you're beginning to see a little bit of a pattern forming between the 2 by 2 case and the 3 by 3 case of moving along this row and then crossing things out and then working with what is left behind after things are crossed out. And this approach to determinants for 2 by 2 and 3 by 3 matrices will be what we use when we calculate determinants of larger matrices. For example, 4 rows and 4 columns. The pattern here is move along top row, extract entries, cross out row and column containing that entry, get the determinant of the submatrix left behind, and then as you do that for every single entry in the top row, then you alternate signs between terms, plus minus. Toward the middle of the course, lesson like maybe 15 or 16, we will use this generalized process to find determinants of larger matrices. So that concludes this lesson talking about arithmetic of matrices. We have in this lesson focused on on matrix addition, matrix subtraction, matrix transpose, and some simple small determinants. You can add, subtract, and scale matrices entry by entry. But if you're going to add matrices together or subtract them, they have to have exactly the same shape and size. They cannot have mismatched sizes. Transpose acts to take a matrice's rows and turn them into columns instead. And the matrix determinant follows a general pattern of stealing entries on the top row, then crossing those entries out to get submatrix determinants and alternating signs plus minus as you move through those terms and through those entries.